Okay, we now do the problem formulation and solution for steady state diffusion in a slab with reaction. So here the species is diffusing and it's simultaneously consumed. As an example, we can think of drug delivery in the brain tissue where you have uh, diffusion of drug from these wafers into the tissue accompanied by consumption. Now notice that this we are interested in a 1D process. Okay, so we want to do 1D slab. Okay, so the governing equations we should start from is the full governing equation for 1D Cartesian coordinate. We are doing the case of a first order reaction. That's why the term normally we write RA, the reaction term has been set at minus K double prime, which is the reaction rate constant. K double prime is the reaction rate constant multiplied by concentration. That's what makes it first order. It's proportional to the concentration, but it's a consumption term. It's being used up. Now, this is it's not an unsteady problem. It's a steady state problem that we want to look at. So then if it is steady state problem, then this one goes, the first term goes. Also, there is no flow in it inside the slab. So the second term also goes. This leads to the governing equation as del square Ca del x square minus k double prime over d times Ca equal to 0. This guy is my governing equation. It's second order. You can see it's second order. So it will need two boundary conditions. So what are they? One of them is the boundary condition at the surface. This one, boundary condition at x equal to 0. This is and this boundary condition is some concentration given. So that is equivalent to whatever would be the concentration in the tissue that is touching the drug. Okay. The other boundary condition is this one. What this implies, concentration at x equal to L, some distance L here, concentration is 0. So as the species is diffusing and it's being consumed, it's expected or it can happen that at some location the concentration becomes 0. So that's my other boundary condition. Now the solution to this governing equation and boundary condition is done in any standard textbook on transport processes, and we're not going to go through the detailed solution. Instead, I just provide you with the solution. So it says concentration as a function of position x. Okay, so this is my solution to the above governing equation and boundary condition. The two parameters that we had, remember we had k double prime over d, and that is in this m. So m equals square root of k double prime over d. So all the parameters, the two parameters of the reaction rate constant and diffusivity are included in this m that you see. From this solution, this is a general solution where concentration is 0 at x equal to L. We can easily show that if L goes to infinity, if L goes to infinity, which just means it's a very thick domain. If L goes to infinity, then you can see that this term, this guy basically drops out, and our solution becomes simply an exponential decay. So this exponential decay solution for concentration as a function of x as an exponential decay is going to be what we will play with in the next few slides, but this is valid only when the domain is thick.